Today will be about field isomorphisms. So if I have a field extension, I say that a k automorphism of L is a k-linear isomorphism from L to itself. Equivalently, I can say that it is an isomorphism of k algebras from L to itself, or an even other way to say it is that it is a field isomorphism that fixes k. And the set of all k automorphisms forms a group because we can take an inverse to an isomorphism, and because we can compose two isomorphisms to get another isomorphism. And this group is usually denoted by G of L over K, and it is called the Galois group. Of L over K. I will need a set of preliminary facts. So the first lemma is if I have two field extensions, L and L prime over K, then I can say that a homomorphism of fields from L to L prime is uniquely defined on the generators. So suppose that L is generated over K by a finite number of elements. And this is a finite extension. And suppose that phi and psi are two k isomorphisms. Then if for every generator, for every I, phi of alpha I is equal to psi of alpha I, then they coincide. In particular, if further L is equal to L prime, and phi from L to L fixes all the generators, then it is the identity, the identity homomorphism. And next, let's take an irreducible polynomial over the base field. And assume that alpha in L and alpha prime in L prime are its roots. Then there is a unique K isomorphism phi from K adjoint alpha to K adjoint alpha prime. So note that K adjoint alpha is a subfield in L, and K adjoint alpha prime is a subfield in L prime. And we don't say anything about homomorphisms between these two fields, just about their subfields, which are obtained by adjoining roots. So for the proof of part A, I can say that every element of L, if L is of this form, is can be expressed as a polynomial in elements alpha 1 through alpha n. In the generators. Then let me compare phi and psi. Then phi of this element, because R is a polynomial, I can use the properties of phi that it is a homomorphism, so it is additive and multiplicative. So I can write this as R, the same polynomial, but instead of alpha 1, I plug in phi of alpha 1, etc. through phi of alpha m. But by the assumption, phi and psi coincide on the generator, so it is the same as applying psi to these elements. And because psi is a homomorphism, it is psi of the original element. So because we can express any element of L as such a polynomial, phi and psi coincide on every element of L. So they coincide. Phi is equal to psi. The second assertion follows from comparing phi to the identity. So instead of psi, let's take the identity homomorphism from L to L, and then psi and identity would coincide on all alpha i's, and therefore they must coincide by the previous fact. And for part B, we know that F is irreducible over K, but alpha and alpha prime are roots. So F is the minimal polynomial of alpha over K, as well as of alpha prime over K. And so the subfield K adjoint alpha, the subfield of L, is isomorphic to K adjoint X mod out by F. And this is further isomorphic to K adjoint alpha prime in L prime. And if we take the composition of these isomorphisms, alpha goes to X here, to the class of X, and X goes to alpha prime. So we get a unique, so we get a K isomorphism phi, and for uniqueness I need to assume that this isomorphism phi takes alpha to alpha prime. And then uniqueness with this assumption follows from part A, because any homomorphism is uniquely defined on by its value on generators, and we have only one generator and a prescribed value, alpha prime. And this concludes the proof. The next useful result is called primitive element theorem. And I'm presenting it here without proof, because in the next two lectures I want to get to the main result of Galois theory. And proving primitive element theorem would probably take half a lecture. So let L over K be a finite extension. And let's assume that we work in characteristic 0. So characteristic K, and therefore characteristic of L is 0. And this is an important assumption that will also appear whenever we use the primitive element theorem. Then there exists an element gamma over L such that L is generated over K by this one element gamma. And this gamma is called a primitive element for L. This is a significant simplification for this lemma, because in part A you would have been checking that phi and psi coincide on, say, n elements, but by the primitive element theorem you can say that there is one element for which you need to check that these field homomorphisms coincide. Now, I want to talk about what fixed fields are. So let G be a group of automorphisms of a field K. So I can think of it as a subgroup of the Galois group of K over its primitive field, over its prime field. So each G in G acts on K by an isomorphism. So G goes from K to K. And the only element G in K that fixes K is the identity element. So G is equal to E, and E is the identity in the group G. In this situation, when I have a group acting on a field, I can define the fixed field of G as follows. It is denoted by K with the superscript G, and it consists of all elements of K that are fixed by all elements of G. So for every G in G, G of alpha is equal to alpha. And the theorem that I can prove about fixed fields is the following theorem. Assume that G is a finite group. And take any element beta 1 in K and consider its G orbit. So G beta 1 consists of all elements of the form G applied to beta 1, where G varies over all elements of G. And let me call all the distinct elements beta 1, beta 2 through beta K. Then I can calculate the minimal polynomial for beta 1 over the fixed field. So I define f of x as the product of all the elements from all the different elements from the orbit. So x minus beta 1 through x minus beta k. And this is the minimal polynomial for beta 1 over k superscript g. And since beta 1 has a minimal polynomial, then I can conclude that beta 1 is algebraic over the fixed field kg, and its degree is equal to the number of elements in the orbit to the order of the orbit. And so from group theory, I can conclude that in particular the degree of beta 1 over the fixed field divides the order of the group, because number of elements in an orbit divides the number of elements in the group. So I will now prove the theorem, and from what I have just said, I need to only prove part A. Okay, proof of theorem. The first thing that I want to check is that F has coefficients in the fixed field. And you can encounter it in later mathematical coursework, that whenever we have a group action and we take some sort of sum or product of elements in the orbit, then the resulting element would be G invariant. So let me prove that that the coefficients of F are G invariant. So I want to act on the whole F by an arbitrary element G lowercase from the group. So I have G of F of X is G applied to X minus beta 1 through X minus beta k. So X is a formal variable, so we don't touch it. And we have then G minus, we have X minus G of beta 1 through X minus G of beta k. And we know that G is an automorphism of K. So G, if we restrict its action on the orbit, B1 through Bk, this is a bijection. And therefore we can continue this string of equalities, then G applied to F of X. It means that G acts on beta i's by a certain permutation, and so if we permute these factors, we get again the product of X minus beta i's, which is equal to F of X. And so when a homomorphism G keeps a polynomial the same, it means that it also fixes all the coefficients. So all the coefficients of F are fixed by G, and this G was chosen arbitrarily. So all the coefficients are contained in the fixed field, which is exactly saying that F is a polynomial with coefficients in the fixed field. Okay, we proved this part, and now to conclude that it is the minimal polynomial, I need to show some sort of minimality. So let H be the minimal polynomial for beta 1 over k superscript g. So beta 1 is a root for h, but h is irreducible over kg. Okay, but we know that field isomorphisms take roots of polynomials to roots of polynomials. So for every g of beta 1 is also a root of h. And so when we vary g lowercase over all elements of the group, we get all beta i's. So all beta i's are roots of h, and they are all distinct. So each x minus beta I, the set of these linear polynomials, all of these polynomials are mutually coprime, and so they divide h, and their product would also divide h. So f, which is the product x minus beta 1 through x minus beta k, also divides h. But h is an irreducible polynomial, irreducible monic polynomial, and f is monic and divides h. So f should be equal to h. So f is the minimal polynomial for beta 1. So this theorem showed that every element of K is algebraic over the fixed field of a certain finite group. And whenever we have a situation when all elements are algebraic, we call this field extension algebraic. So we say that a field extension L over F is algebraic if any element alpha in L is algebraic over F. So by this theorem, if G is a finite group of automorphisms, K, then K over K superscript G is algebraic. And another example is that if L over F is finite, then it is also algebraic. We proved it in one of the first lectures about fields. If L over F is a finite extension, then for every element alpha, when we take powers of this element alpha, 1 alpha, alpha squared, etc., they will be linearly dependent because L is finite dimensional over F. And it means that we will get some polynomial that vanishes at alpha. And the third example of a field that is algebraic but not finite is if I take Q bar. It is the set of all elements in complex numbers that are algebraic over Q. So this field, this set will form a field, and it is an algebraic field extension. But it is not finite, because we can take larger and larger roots, complex roots of unity in C, and these roots of unity will have larger and larger degrees. So it cannot be finite, because for any finite number we take a root of unity of a larger degree than this number. We know that K over Kg is algebraic, but because the group G is finite, we also want to show that this is in fact a finite field extension. And this result is called fixed field theorem. If I assume that K is a field of characteristic 0, and G is a finite group of automorphisms of K, then the extension K over K superscript G is finite, and its degree is equal to the order of G. I can start the proof by first observing that by this theorem below, K over Kg is algebraic, and any element beta in K has a degree over the fixed field that divides the order of G. So it is in particular not greater than the order of G. And so we saw that in our example of an infinite algebraic extension, degrees of elements can be arbitrarily large, and in fact I can prove a lemma that if L over F is an infinite algebraic extension, and characteristic of these fields is equal to 0, then there exist elements in L of arbitrarily large degrees over the base field F. So for the proof of this lemma, I will show the following. So assume that we found an element alpha in L of degree over K equal to n, then I show that for every such element we can find an element of strictly greater degree than n. And then by continuing increasing the degree, we get arbitrarily large degrees. So then f adjoint alpha, and here of degree over f. Then f adjoint alpha is a finite extension of f, and then there exists an element beta in L that does not lie in f adjoint alpha. And so K adjoint alpha and beta is strictly bigger than f adjoint alpha and beta is strictly bigger than f adjoint just alpha. And we know that by primitive element theorem there exists gamma such that K of alpha beta is in fact generated by this one element gamma. This is again f and f. And so we can compute the degree of gamma over f. It will be equal to the degree of the field extension that we get by adjoining gamma. But this field extension is strictly larger than the extension obtained by adjoining alpha. So the degree of gamma will be strictly bigger than the degree of alpha, which is n. And so we found an element of strictly larger degree. And again, by finding some other element gamma prime that does not lie in f adjoint gamma, we can take a primitive element of this bigger finite extension, which would give us an algebraic element of a larger degree. And so from this lemma, it follows that since all the degrees of elements in K are bounded by a finite number, this extension cannot be infinite. So K over K superscript G is a finite extension. Again, we are working in characteristic 0, so we can find a primitive element for this extension. So there exists gamma in K such that K is obtained from the fixed field by adjoining gamma. And now I want to show that the degree of gamma is equal to the order of G. So for this, I use the previous theorem that the minimal polynomial for gamma over the fixed field is equal to x minus gamma times x minus gamma 2, etc. minus gamma n. where gamma and gamma i's are elements of the orbit of gamma. Now I claim that gamma has trivial stabilizer in G. So if G, lowercase from the group, is such that G of gamma is equal to gamma, then we know that G fixes the only stabilizer in this field, the only generator of this field. So by the very first lemma, we have G that fixes all the generators. And so we get that G is the trivial automorphism, the identity automorphism of K. So we denote it by we denote the identity element by E lowercase in G. Which means that the order of the orbit is equal to the order of the group. But the order of the orbit is equal to the degree of the minimal polynomial, which means that it is the degree of gamma over the fixed field. And since gamma generates K, this is equal to the degree of K over its fixed field. And so we proved the theorem.